RockTrue Science is a cross-cultural response to the lack of diversity in STEM fields. STEM stands for science, technology, engineering, and mathematics. RockTrue Science is designed to serve the intellectual need of fallen man while serving the desire for interdependence to better understand our physical world while still pursuing spiritual growth. Rock True Science speaks to inspire, enlighten, and highlight upcoming and established local and international kings and queens of STEM fields while promoting Black consciousness and awareness of who we are and to whom we belong. Good evening. Good evening. So I got a little bit of bad news. So I got an email a little bit earlier today about my male science experiment kit, and it's delayed. So we won't be able to do our experiments today, but I will still go over the science behind them, and a lot of that is some of the acid-based chemistry. So we're going to get into that topic as well, and we are going to talk about halogens today as well. So let me see. Should I start with the? I guess I could start with the chemistry behind the experiments we would have done. So they're really cool experiments. So we're just gonna have to do that at the start of the next show. Because trust me, y'all gonna want to see this. Okay. And as you remember, last week we did do a quick experiment with the walking water. That was so cool with the different colors. And so these experiments were all going to be very colorful as well. However, instead of it just being colored water, most of the chemistry behind what was going on here was oxidation reduction. And we talked about that in a couple of the earlier episodes where we mentioned mostly with, I believe when we were talking about the alkali metals, I mentioned that because they tend to be involved in a lot of that oxidation reduction type situation. And go figure, sodium hydroxide is usually a really big what is that base? It's a very basic oxidizer. So because the hydroxide and the oxygen, and they tend to do their little thing. And so the first experiment, which uses this concept, would be the blue bottle experiment. So the experiment has methylene blue, which is an indicator, and it's called methylene blue because it's blue. So it's an indicator for for this oxidation reduction reaction. So when it is in its in its normal state, it is blue. So when it's blue, that means it is an oxidizer. So the oxidizer is the one that is gaining electrons. So it is being reduced. So oxidizing means it is pulling electrons to it very strongly. So an oxidizing agent is grabbing for electrons. And then it would be sugar. So yeah, sugar, which is C6H12 O11. So that's 6 atoms of carbon, 12 hydrogen atoms, and 11 oxygen atoms. And then when it dissolves, it dissociates into various ions and things like that. But what it also does is it gives up these electrons. So it's losing electrons. So it is a reducing agent. So it is the one that is giving the electrons to the methylene blue and making it blue. Now, what happens in this experiment is when you allow this system, because you put the cap on the bottle and you put your methylene blue in there with your sugar water, and it's in there and it's blue, and then eventually it becomes clear. So the methylene blue, once it gets oxidized, it turns clear. It becomes colorless. And so when you shake the bottle, it turns the methylene blue again, because the methylene blue is once again it's reactivated by the electrons in the oxygen in the little space of gas at the top of the bottle. So see, this is why we do experiments, so you can see what I'm talking about. But experiments are very useful because they give a practical application of the science. So you can see how oxidizing and reducing agents are useful in a practical situation, hence the experiment. So I'm not sure when would you want to change like colors and something, like probably just cause it's cool. Then the next experiment was going to be the magic liquid. So this experiment looks kind of similar to the walking water one, except instead of putting paper towels in the cups and letting the water walk along, we are using acid-based chemistry. And so that is a topic that we're going to cover a little bit later once I go over this and we get into the halogens. So the science behind this is you have five. You have 5 different cups, and each cup has an indicator in it. So this indicator has a 2 negative charge on it. So it's going to accept protons, going to accept H plus ions. And the way you make these H plus ions is by creating different levels of acidic solutions. So, and then on the other end of it, where you get the green and the blue color in the indicator, those are basic solutions. Excuse me. And so your indicator is going to turn colors depending on what ions it binds to. So if it binds to the hydrogen ions, then it's going to create red, orange, yellow colors. If it binds to hydroxide or lower level of no, if it doesn't bind, because this indicator is initially blue in its natural regular state, it is blue. And so if it doesn't bind to hydrogen ions, it's going to stay blue. And then you have the mixing of colors. So you have your primary colors, which is red, yellow, and blue. But the way that you get the orange and the green color is a mixture of these colors. So getting into the chemistry of that, your first cup has sodium hydrogen sulfate. That is your proton donor, your acid. And then when it's dissolved, this indicator ends up being matched with 2 hydrogen ions. So this acid dissociates completely, gives off a whole lot of hydrogen ions. And so the indicator is able to pick up a ton of hydrogen ions and it turns red. And this completely neutralizes the indicator. Like I said, the indicator has a 2 negative charge on it, so it can only pick up 2 hydrogen atoms, or well, they're ions in solution. So 2 hydrogen ions, and then it fully neutralizes the indicator, and it makes the solution red. Then in cup number 2, we have, I think that's citric acid. That's citric acid. What is that? Citric acid.
I thought it was love.
Don't quote me on that. It's probably citric acid. I had that written down somewhere, but it'll come back to me. But this is a quick overview, because like I said, I'm gonna talk about it as I do these experiments when I finally get in the experiment kit. But I want to prep y'all for it, so you know your mind is like I remember that from last week. So in this case, when this dissolves in water, this is a weaker acid. So it's not going to give as many hydrogen ions in solution for the indicator to bind to. So it's really only going to bind with 1 hydrogen ion. So you have, it'll be like a mixture. So it's not enough to bind completely to all of the indicator. So some of the indicator will be used up and bind with 2 hydrogen ions, making a red solution. Remember in the first one, the indicator turned red when it has 2 hydrogen ions. However, there's not enough hydrogen ions in this solution to bind all of the indicator completely. So you have some that has 2 hydrogen ions and some that only has 1 hydrogen ion. And that is going to make a yellow version of the indicator. So red and yellow make what? Orange. Okay. See how that worked? We just made color with acids. Okay. Then the third cup is yellow. So this is like a strange space. So water is slightly acidic because it does have hydrogen ions in it and some hydronium ions, which is the H3O plus. So that's what makes it slightly acidic. So there are hydrogen ions, there are OH minus ions, there's H2O, and then there's H3O plus. So because there's H3O plus and H plus ions, that is why water is actually slightly acidic in its natural equilibrium state. So when you put this indicator in water, the water is going to be a little bit more orangish yellow. So it's going to be a more of a darker yellow than a bright yellow like this third cup is going to look. So that's why you don't just mix it with water and be like, boom, there's the yellow cup. Like, no. So in this case, some of the citric acid and there's a sodium carbonate that is mixed in. So the sodium carbonate helps basically keep the citric acid from dissociating even further. So now you don't have any indicator that is bound to more than one hydrogen ion. So all of the indicator is going to look yellow. Then in the fourth cup, you're going to get green. So now we're moving into the basic range of pH. And in this solution, you're dissolving sodium hydrogen carbonate. Yeah. And that is actually, that's sodium that's bicarbonate. So that's actually the buffer that's in our blood. That's what keeps our blood pH at optimum levels. And we're going to talk about that a little bit later too. Buffers. All right. So this does not fully dissociate, and it actually the sodium kind of binds up some of the hydrogen in there. So you end up where you don't have as much hydrogen released because there's only one H ion to be released from this compound. So it's NaHCO3. That's what it looks like. So there's only one hydrogen in there to bind to the indicator. So you're going to get yellow. And then once all the H is used up, you have blue indicator in there. So guess what? Yellow and blue make green. And then in the fifth cup, you're going to have your sodium carbonate, and then that's going to dissolve. So this is the one that we mixed in with the sulfuric acid in the yellow cup. So this doesn't have any, no, not sulfuric, citric acid. I want to say that's citric acid. Don't quote me on that because I'm looking at this and I'm like, I should have wrote down what that acid was, but it's a weak acid. So the salt, the kind of salt, the base creator is the sodium carbonate. And in this, you're going to get OH minus ions. So there's no hydrogen ions in this solution because the carbonate comes through and messes that up. So your indicator stays blue. So when you mix that, when you mix your indicator into this liquid, you're going to get blue. And that's the chemistry on that one. And then there was the color changing milk. So the reason why milk is used in this experiment is really just for a contrast background because it's white, but you can absolutely try different color solutions because for the most part, this is about the chemistry of the soap. So soap is something that creates a film on top of a liquid surface. And so that's really why soap, it has those grease fighting powers because it makes this bubbles and things around the grease in the water, and it basically separates it with this film. And so we're using that idea to make pretty colors. And so then once you add this soap to this mixture of colors on top of the milk, is going to make the colors kind of disperse in these cool patterns. So that's, something fun we can play with. And then in the fourth, I know they were sending a lot of experiments. I really like this, so I can't wait. So the fourth experiment is acidic patterns. And in this one, it is using thymol blue, which is a pH indicator. It turns red in an acidic solution, and it turns blue in blue in a basic solution. So with this one, we're using the sodium hydrogen sulfate as our acid, our acidic solution, so our acid creating solution, and then we're using sodium carbonate as the base creating solution. And so with this, you're gonna add them to different areas of I'm assuming they're sending like a little petri dish, and you pour some of this indicator in there, and then when you add different amounts of this acid or base to different parts of this petri dish, you get this different mix of colors, and then as they collide, they begin to neutralize each other, and so you go from red and blue to like you get greens and yellows and oranges in there as it starts to equilibrate and neutralize itself all over. So yeah, I'm excited about that. It's gonna look real fun, real fun. And I believe some of these I actually did like a slightly different version of these in my Gen Chem lab in college. So yeah, this is fun at all levels. All right. So now we're going to get deeper into the acid-base chemistry. It's not a whole lot to go over. It can get real hairy real quick, but we're just going over the basics. All right. Oh, no. I'm just talking about all the other stuff. So yeah, so y'all can get situated before we get into the halogens, because we got some cool videos I want to show y'all, because it was some stuff that I learned about fluorine that I didn't know, because it is so reactive that not a lot of people want to deal with it, and it's highly toxic as a gas. So yeah, people not really trying to risk their life like that for some fluorine. But I was able to find a video of someone who did. So let me know when y'all get situated, and then we can get into that. But until then, we have plenty of other stuff to talk about. No worries, okay? So acid-base chemistry. So when you hear acids and bases, I'm not sure like what kind of comes to mind, especially like on the base side, because I think acids tend to have more of a kind of common awareness, mostly because of like the corrosive stuff like sulfuric acid, hydrochloric acid. Like people have kind of heard about those and know that they're fairly dangerous and corrosive. But yeah, your stomach acid is actually hydrochloric acid, and that's a pH of about 1. So anywhere from 1 to about 3, your stomach acid is extremely acidic. So you have to have a special lining on your stomach that prevents this acid from eating away at your stomach, because that is absolutely something that can happen, and it's very corrosive, extremely corrosive, and it tends to have different what do you call it, MSDS labels and safety labeling and all of this stuff. So when you work with these chemicals and things like that, especially in an industrial setting, everything has to be labeled, and it has to have some type of safety warning and labeling on them for handling purposes, and also for shipping. There's different transportation laws and things for those type of substances. Even in small amounts, everything has to be labeled. But when you get a stomach ulcer, that is why a stomach ulcer is a problem, because a stomach ulcer is essentially a small tear to a hole in your stomach lining. And that's a problem, because then the hydrochloric acid in your stomach can eat away at even the smallest little gap into this unprotected area and make it worse. So that's why, keeping your stress levels down, eating a nice wide variety of foods and keeping your gut bacteria healthy is useful, because your gut bacteria actually help with keeping that stomach lining healthy and keeping you and your cells protected. So for the most part, there are actually three different definitions of what an acid or a base is. The most common is the Arrhenius, and probably the simplest definition, and that's where you get these protons moving around. So the H plus ions I was talking about, that's what's moving around. And then in bases, it's the hydroxide, so the OH minus ions. That's what creates bases. And so these weak acids have, like I said, lower concentrations of these H plus ions in solution, and weak bases have lower concentrations of OH minus ions in solution. Strong acids and bases completely dissociate. So dissociate means they completely break down from, like NaOH, sodium hydroxide is a strong base. When you put it into water, it completely dissociates into sodium ions and hydroxide ions. There is no NaOH hanging out anywhere in a solution of water, unless there's not enough water to ionize your sodium hydroxide. So that is where concentrations come into play. So the amount of water or a solution that your acid or your base is dissolved in is going to determine the concentration of the hydroxide or the hydrogen ions found in solution. And there's who is that? There's a couple of different ways to calculate that, and that's where I'm saying it gets real complicated when you actually try and calculate the specific concentration of those solutions, which unless you actually work in science, you will probably never need to do. So so that's why we're probably not really going to cover that, but you can definitely look that up if it's something that you want to know or you want to try out. You can definitely do that, and it's yeah. It can get weird, mostly just because depending on, like I said, if it's not a strong acid or base, then the numbers get hairy because it's not completely dissociating. So you can't be like, oh, I put this much NaOH in, so this much OH should be present. You can't do that with weak acids and bases. You have to, yes, it's some stuff you got to do in there. I don't even remember the math off the top of my head because that was a struggle for me. Even when I was learning it in school. So moving on. So then you have your Bronsted Lowry acids and bases. So the Bronsted Lowry acids donate protons. So we're not talking about H plus. We're talking about actual protons. With hydrogen. So the whole hydrogen goes over there, not like just the ion, like just the whole hydrogen goes over there, and then the bases are accepting those hydrogens. So they're slightly different in that you're not looking at two different types of ions. With the Arrhenius acid and base, you have a hydrogen ion, and you have the OH minus ion. And in the Bronsted Lowry, you're only looking at the movement of the hydrogen ions. And then you have Lewis acids and bases, and those are the acids donate electrons, electron pairs, and then the bases accept electron pairs. So you can see how that's kind of a strange definition. That's also why the general public doesn't really recognize that when they're talking about an acid. When they're talking about an acid in regular Joe Schmo walking down the street, I guarantee you they're referring to an Arrhenius acid or base. Mostly because that concept is a lot easier to kind of take with you somewhere. Because like I said, there's not a whole lot of ways that you can check electron movement. So 9 times out of 10, people are using an Arrhenius definition unless otherwise stated. And so we can talk about some examples on the pH scale. So a pH of like 0 would be battery acid. Battery acid is extremely corrosive. That's why they talk about properly disposing of your batteries. That's also why it's bad if your battery is leaking, or if you do anything that makes a battery leak. It tells you not to mix battery types, like battery bands, brands of batteries and things like that. Like there's so many different things like to avoid making battery acid leak out of a battery. And I suggest that you keep that in mind. And that's also why you're not supposed to dispose of batteries in your regular trash. I don't know anywhere now, but Circuit City. Yeah, I'm that old. Circuit City, I know for a fact, and maybe Best Buy still. Is Best Buy still around? I don't know. All these places keep closing on me, so it's like you got to keep finding new names for for all of the stuff, because it's like they can't keep an electronic store open. But most electronic stores, for the most part, especially if they're big chains, they actually had battery collection bins for old batteries so that you can dispose of your batteries there, and they will safely dispose of it for you. And maybe Office Max or Office Depot, they might still do that. I don't know. Don't quote me on that. You can probably check their website. But you can also check like your local I think like the poison people, the people that you call for like if you get poisoned, that number, they tend to have information on proper disposal of electronics and batteries and things like that. Mostly because electronics like cell phones, laptops, and all that stuff have batteries in them, and they need to be properly disposed of because it's hazardous to the environment, okay, and extremely dangerous. Stomach acid, that's your pH 1, as I mentioned earlier. Vinegar has a pH of 2. Surprise, surprise. Yeah, it's pretty acidic, but not very corrosive. So the zeros and the ones, extremely corrosive, tend to be quite corrosive. Vinegar is not corrosive, mostly because it acts kind of like a buffer. Like it doesn't completely dissociate, so it's not like all in and then a lot of times we tend to dilute it and other things and stuff like that. But it is a great defense against mold. So if you need to clean a moldy something, soak it in some vinegar water. Orange juice has a pH of 3, so that's that citric acid. Tomato, pH of 4, so tomato is actually slightly acidic, which is why tomato sauces and things like that tend to have acidic properties and can stain your teeth pretty well as well. And black coffee is a pH of 5, which is acidic, and that's also why coffee stains your teeth, because it's acidic. So it actually breaks down the enamel in your teeth, and that's how the staining gets in there. So to protect your teeth, you brush your teeth with toothpaste, which is basic. And so the toothpaste neutralizes the acids produced by the bacteria that feed on the food and debris left in your mouth after you've eaten and all of that junk. And also food itself, as you can see, is acidic itself. So you're creating an acidic environment in your mouth, which is why they recommend you brush your teeth after every meal, because it protects your teeth. It neutralizes the acid in the food and the bacteria, and it cleans your mouth. So, that's how you fight the good fight against bad breath. All right. Saying this for the people that don't socially distance, because I would say that was probably one of the best things that came from social distancing is I ain't got to smell your breath. I know it was a little petty for that, but that was seriously a win, and check that win in my column. Okay. 7 for water. Like I said, water is still slightly acidic for the most part. It's like kind of like between like 6.9 and 7 but it's like, in general, water is considered a neutral substance, mostly because, like I said, it goes in and out of these different phases and things like that. And then also the temperature of the water determines all of that stuff too. So, seawater is actually slightly basic. You know why? We know why, because it's salty. Okay, the salt actually makes it a little bit more basic. Okay, there's other things dissolved in the seawater that gives it more of a basic characteristic. Baking soda is basic. It is pH 9. Indigestion tablet. So the indigestion and we kind of talked about this last show or the show before last with bismuth. Bismuth is the main ingredient in Pepto-Bismol. Okay, pink bismuth, and pink bismuth is pH 10. Okay, and that's why it settles your stomach down. It's like, oh, chill out, and it gives you time to, catch your bearings. But you don't want to like live on those things, because you need your stomach acid to be acidic so that it can dissolve your food. So I would suggest, if you are having indigestion and stuff like that, you wait until after you've digested your food first. Like if you get in, like right after you eat, wait an hour or two, okay, for your stomach to clear out. And if it's not over by the end, then take you one. Hey Ty, then take you some Pepto-Bismol, or an indigestion tab like Tums and stuff like that. Then do that. But I wouldn't suggest doing that with a stomach full of food, because I just feel like that's counterproductive. Like your stomach acid needs to be acidic to break down your food. And then if you put something that neutralizes your stomach acid, what is your stomach acid not doing? Breaking down your food. And then that's also why when you take those indigestion tablets, they have the little side effects on there. It tends to be constipation. That's why, because you have neutralized the stomach acid that breaks down the solids and make them easier to be digested by your intestinal bacteria. And then if you have these mostly solid chunks of food going through there, as opposed to the mushy paste that usually, or liquid that usually comes through, because your stomach acid can dissolve protein and meats and things like that down into liquid. Like, hey, Marley King. Yeah. Uh-huh. All you meatheads, eat more fiber. Yes. That is feeding your bacteria. Okay. You normally take baking soda for upset stomach. Yeah, that works too. Yeah, I said, yep, there's right there just before that. Same difference. And also, I guess it depends on your level of discomfort and all that too. But baking soda and a little bit of water, that works just fine too. And yeah, and also just eating more fiber, like Marley King said, that helps with indigestion. A lot of times, indigestion comes from you having like a really acidic situation in your stomach, and then like you add in more stuff to it, and it's just like you don't have that balance. And also being too full. So a lot of times, like if your stomach is like really full of stuff, and then it's like you trying to digest stuff, you put some water in there and all that stuff, and it's like, oh, it's right there. It's like, and you get that heartburn feeling. Like, yeah, I don't like none of that. Fatty foods do that as well. So eating a lot of fatty foods can cause a lot of indigestion and heartburn. So yes. Then you have pH 11, which is ammonia, that stinky stuff that you're not supposed to mix with bleach, because it creates chlorine gas. So that's why you don't mix those. Chlorine gas is toxic. Just like how I mentioned about fluorine. Fluorine is like super duper toxic. Like you can, like, no one can ever say what fluorine gas smells like, because whoever smelled it died. That's the honest truth. Okay. Don't worry. We getting, I told y'all the halogens are so, hey, I told you. So we getting there in a minute. Give me a sec. Okay. Then soapy water has a pH of 12. And then the reason why soaps, so most bases, they have like kind of a slippery feel to them, like soap, because they alter the structure of proteins. So proteins, for the most part, are like fatty acids and things like that. So they tend to have a hydrophobic, which means they repel water, they don't like water, and a hydrophilic portion that loves water. So like triglycerides has a hydrophobic tail, which is the long fatty chain, and then the hydrophilic head, which is, the part that's usually oriented to the outside of the cell. So like your regular inside your body cells, like the lining of your blood vessels, for instance. Your blood is a water-like solution. Basically, we'll call it that. It's a water dissolved solution. So there's water in your bloodstream and all that stuff, and the cells that orient towards your bloodstream, the outside of them has their hydrophilic head towards the outside, and then inside the membrane is these fatty chains that is hydrophobic, and so they orient towards each other, and that's how soaps work. Those little hydrophobic parts turn away from water, and that's why stuff that gets surrounded in soap suds and things like that separate from water very easily. So that's how they clean the grease off of stuff, get dirt off of stuff like that. It makes it where the stuff is trapped inside something that doesn't like water, and you can just rinse it off. And then you have bleach at a pH of 13, and drain cleaner is very, very basic. It is a pH 14. So very basic things are also corrosive. Okay. That is how drain cleaner works. It dissolves organic substances that is in your drain, clogging it up and all that stuff. It dissolves the stuff in there. Okay. That's how it does its job. And because it's a base, it tends to alter the structure of the proteins and the stuff, the gunk and stuff that is dissolving away quite easily. If you poured acid down your drain, like a really strong acid, you might make that stuff catch fire instead. So that's why they don't make drain cleaners acidic. Plus, you need the more acidic something is, the more a special container needs to be used. I think it's like polyether something. Hold on, I'm gonna look it up. Let's see, what we'll do hydrofluoric acid, because hydrofluoric acid is basically considered the strongest acid in existence. So hydrofluoric acid won't eat through plastic. It will dissolve metal, rock, glass, ceramic, so like organic stuff. Okay, so that's why they tend to use bases, because they're much easier to control, and then they don't give off horrible gases. So acids tend to dissolve things and react with metals. So if you're pouring drain cleaner down your drain, what are your drains made of? Metal. And if you have an acid in there that's reacting with the metal, guess what's coming back up? Gases. Gases are flammable. So that's why acids tend to dissolve things and then burst into flames if they are, not dilute. I learned that lesson the hard way. I was in my chemistry science class and I spilled some sulfuric acid on my bench top. And then instead of pouring water on it first to dilute it like I was supposed to, I threw a dry paper towel on top of it. And the paper towel started to dissolve a little bit, turn brown, and then burst into flames. So yeah, quickly learned that's not how you do that. So with the acids, they readily interact with metals and they produce hydrogen gas, which is extremely flammable, and a salt. So like sulfuric acid could probably interact with magnesium quite readily. And I believe we did that. That was one of the experiments we did a couple of weeks back. I want to say probably last month, where we lit the oxygen gas on fire from the magnesium. Oh no, it was aluminum. It was aluminum, and it was dissolved in sulfuric acid. And so the sulfate, you got aluminum sulfate, that's the salt. And then the hydrogen gas bloop, 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 bubbled over into the water test tube, and the gas floated up, and you had pure hydrogen gas and oxygen, I guess, on the top. So it was forcing the gases out of the water, and then you light that gas on fire. Boom. So yeah, that tends to be a very common reaction, especially in industrial processes and things like that. So they tend to collect those gases for other things because they're a great source of clean, clean fuel, propellants, and things like that. And that's also why hospitals are very careful about how they store their gas, because they tend to have a lot of oxygen tanks and hydrogen tanks under pressure. So that makes them extremely flammable and explosive, especially under pressure. And then we have our acids can react with carbonates. And when they react with carbonates, they produce CO2 gas and salt and water. So that is, I believe, yeah, I think that's all I got for y'all on the acid bases. If y'all have any like questions, comments, concerns about that topic, I will gladly go deeper. But I feel like that's good to get us, aware of our acid-based situation. All right, so is this the okay, so this is the fluorine bit. Yeah, I know, I'm way too excited about it. So I try not to do too long of videos because you could definitely lose interest, but no, you're gonna want to see this. So this is fluorine in the lab, and this is the gas. So this is the very toxic fluorine gas. It only takes 0.1% of it in the air for it to be deadly. So if someone drops a tube of fluorine gas in a small room, everybody could possibly die. So yeah, that's how toxic it is. So go ahead and play that clip. Oh, okay. Oh, but some more stuff about fluorine. So fluorine gas tends to have kind of like a yellowish color, I would say. It's not completely colorless, but like I said, they don't know what it smells like because anyone who smelt it died. Whoever smelt it dealt it. Whoever smelt it died. And then bromine. So chlorine tends to be kind of like a greenish gas, but fluorine and chlorine are gases in their natural elemental states. So oh, okay, because I'm trying to who? Right, I got you. Okay, yep. Yeah, we all learning at the same time. It's cool. And bromine is actually a liquid in its elemental state, and then iodine and astatine are both solids in their elemental state. So this is one of the only groups in the periodic table that has all three phases in its in this collective grouping present in their elemental forms. Most of the other ones exist as either solids or gases. I think, yeah. I think mercury is the only other regular thing that's a liquid in its elemental form. We can't hear.
I'm in the office of Professor Eric Hope. There he is. Who is one of the country's specialists in fluorine chemistry, and he knows how to handle this terrific element safely. I have no idea what to do. I'm quite excited to see what happens.
One of the things you said in that original video was on YouTube was that you've never won. Fluorine was one of the few elements that you haven't seen. So I thought there are actually relatively few chemists who have seen fluorine. So what I'm going to do is try and show you what's actually produced and show you elemental fluorine. Fluorine is slowly released, and you can see the pressure so go up.
The reason that people know that is one of the really reactive elements. It will react with all the elements of the periodic table except neon helium. It will react with gold, it will react with silver, it It'll react with platinum. Platinum hexafluoride. It's bright red. It's a gas.
Okay, so fluorine is going into the apparatus. It's going into this tube. Martin, you can't see anything. You can't see anything at all. And that's because
Okay. Technical difficulties real quick. It's okay. It's all right. But while we're waiting on that one, we'll finish up. What was I talking about? So chlorine gas was the first of this group to actually be isolated and identified. And I believe it was also one of the first like elements in general to be isolated and identified. So that's pretty cool. And I believe it also has something to do with the fact that this group is so reactive. So obviously the stuff that's the most abundant and the most reactive is going to get the most attention. You know, the squeaky wheel gets the oil type situation. So the most reactive element gets gets the identification. And it's mostly used to generally used to purify water. So like as we see in pools and things like that, it's used to
as a matter of fact, for
kill
what it's worth,
bacteria,
Grammarly can,
viruses.
yeah, that's long. We can get.
It was much more exciting than I thought. You see the flames. Our first video of fluorine was a bit disappointing. There wasn't any, just a few bits of glassware and some funny stories.
Okay,
so at the
it
moment,
seemed to be going.
I'm in the office of Professor Eric Hope,
But pretty much what you just did, that's all we're doing. I'm going to go ahead and like this. You got one up that's doing a share screen.
Safely.
If you want to, you can stop sharing that screen and it'll get rid of that extra bubble of yours. So you see how I got to, you got to
on YouTube was that you'd never. Fluorine was one of the few elements.
The one that's yours with the extra video feed, you can get rid of it. You can stop sharing.
And so what I want to do is try and show
stop
you
your screen share.
Actually produce and show you
there
elemental fluorine.
It worked. Okay.
Fluorine is slowly released, and you can see the pressure slowly going up.
The reason that people know about fluorine is because it is one of the really reactive elements. It will react with all the elements in the periodic table except neon and helium. It will react with gold, it will react with silver, it will react with platinum. Platinum hexafluoride is bright red as a gas.
Okay, so fluorine is going into the apparatus, it's going into this tube. Martin, you can't see anything, can you? You can't see anything at all. And that's because
hold on, I don't know how long this is.
There's only a little under 2 atmospheres of fluorine in there. It's a very pale yellow color as a gas.
A bit disappointed, but I suppose it's like oxygen or nitrogen, you can't really see it. But perhaps if we condense it as a liquid, then I'll see it properly.
Okay, so I'm now going to cool this down with liquid nitrogen to minus 196.
About the other stuff, while this video is still playing. Any questions
It'll
about the other stuff, like the comments or the banners or the brand or?
Okay, Martin, do you want to help me with this? So what I want to do.
Do you see above everybody's picture? You see the layout?
Slide it away. And back up again. And there we have nearly 2 inches, maybe.
So those are like the different types of layouts that we have with, depending on how many people on the screen. And you pick the layout that's for you. And then you can also like really grab somebody and put them into really a different space. So if you were on the left and I wanted you on the right, I can switch you into more. You feel me? So you would actually touch.
Basically,
you would touch the screen. The square where everybody is on the screen that's showing the screen, and you would switch people around that way. So technically, like I can move you, hold it, and drop you over. So switch me and you again. I just switched us, and I switch us back.
It's a metal scouring pad. I'm
hold on to yourself and drag yourself to where I am. It should be blue. Any of the switches. Yep.
It burnt a hole right through the iron wool. It's extraordinary. The iron looks as if it's rusted. But
go ahead to the banner and stop that banner or change it.
Maybe a bit of iron oxide from the hot iron.
And the banner is scrolling at the bottom.
Well, the reason that fluorine makes such strong bonds is because
or change it.
It is a small atom.
Yep.
And the nucleus.
If you wanted to, you could change or put something else. Go ahead to branding, go to the logo at the top, change dot to something. It could be the RockTrue one or whatever it is.
Don't shield this nucleus. So it is very so-called electronegative. It attracts electrons to itself from other elements.
I've changed the prop now for some just normal barbecue briquettes. So this is pure carbon.
So we haven't done anything. This is coal charcoal and coal gas, and the gas just touching it is enough to start the fire.
Now you see it's four of us there, and it's boxes inside of the box, right? So one side it got the 3 dots, the other side it has. If you hover over it, it says full screen layout. That's because you're gonna put that person or that clip in full screen. So go ahead and put the video I'm playing right now in full screen.
Then the fluorine forms hydrogen fluoride and it reacts with the water.
So so it's dots on one side. On the other side, it's like a little smaller camera picture. If you
equipment made out of metal, usually nickel.
There you go. There you go.
And the fluorine
reacts
with the surface.
So then, when this video's over, you can remove it. You can remove the video when it's over.
So this is again fluorine
or
sulfur, so
depending on what it is that you're doing, you remove the video. Depending on what's in this box, you can move it to somewhere else or change it from the full screen layout to something else.
So that's like when somebody's talking, and I notice sometimes you'll make them beat it.
Yeah.
That's what you do.
Yeah. That's what we do.
Fluorine
we bring them to the forefront. Yeah.
Being very reactive and very dangerous and something to be careful about. But aren't there fluorine atoms in my toothpaste?
There are. Your toothpaste contains fluoride. And just in the same way that you can eat sodium chloride table salt, which contains chlorine, you can use fluorides. And once the fluorine has got an extra electron, for example, from the tin in tin fluoride, which is often used in toothpaste, or sodium fluoride, it's got what it wants, and it's not very reactive. And the way it works with teeth is that the enamel of your teeth is a compound of calcium called apatite, which normally the apatite in your teeth can dissolve quite easily in acid. For example, if you eat sweets or drink some fizzy drinks, they have enough acid to start dissolving the surface of your teeth. But if you brush your teeth with fluoride,
our commercial video clips,
apatite, which contains
it's okay.
Some of these are replaced with fluoride, and you make a material called fluoroapatite, which is much less soluble in acid, so it can't be attacked so easily, so you don't get holes in your teeth.
So go ahead, sis, remove it. Remove that video, it's over. Remove it from the screen. Boom. Now. So the whole time we've been just talking through this. The whole time we've been just talking through it.
Hey, I mean, I figured y'all. Hey, y'all got to do what y'all got to do.
I ain't even realized that the whole time though we've been like talking.
I mean, the video was more so like a visual thing because I just thought that was so cool. They were using fluorine gas, so it was fluorine gas under pressure.
And actresses do when they have to get in shape really fast.
Oh, that's playing in your background. I was like, who was that talking? I was like, where you come from?
I promise the whole time I did not know we was talking. I didn't even.
I didn't know if you knew we could hear y'all.
No, she said, "Doc, you could have waved your hand like, hey."
I wasn't tripping. I was still watching the. I was still watching the video. They weren't really saying much. They were just talking about the fluorine gas reacting with the different substances they were using. So they had some I think it was like some iron wool, like the fire iron that we did with the little wool
Oh yeah.
iron thing, but
I saw
instead of
that when it
just
was burning it.
instead of just using flame and oxygen and setting the actual iron on fire, the reason why it sparked like that is because fluorine is extremely electronegative, and and that's what makes it very reactive. So it was like literally like grabbing on to the metal ions, and the reaction was so fast that it produces heat. And so once it reacts with the metal, it turns into a salt and it neutralizes it. So that's why it's a salt fluorine that's in our toothpaste. When they say there's fluoride in the toothpaste, it's usually sodium fluoride, because it has been neutralized by the sodium, so that it's not toxic and it's not reactive, and you won't die from using it in your mouth. So that's the cool thing about the halides, is that they tend to be neutralized and they become less reactive once they get their little happy place with their extra electron that they need. So they're very reactive because they're almost a noble gas, but not quite. Like, you know, that one like imitator that be hanging around in the background, like they almost like you, but not quite. But they just gonna do whatever they can to get that one thing that they missing to be like just like that's what fluorine is. But because fluorine is really small, it doesn't have complete proton shielding from its positively charged nucleus. So the electron coverage isn't enough to keep it from being extremely grabby, because it has this positive charge that's kind of showing through its very light proton coverage. Now the larger elements like chlorine, iodine, astatine, bromine, those are bigger and they have a lot more levels of electrons around its nucleus. So it's not so reactive, but they are still quite reactive, but not as much as fluorine, because like I said, fluorine doesn't have a fully covered positively charged nucleus. So that's what makes it extremely grabby and very, very reactive. It's pretty much like the most reactive, the most electronegative element known to man currently. So yeah, it definitely holds that top spot, number one spot. And it reacts with pretty much everything, like everything, like fluorine regularly reacts with everything, except I think it's like one or two things that it doesn't. Oh, hydrogen. No, not hydrogen. Helium and neon gas are the only two elements that it does not react with. And those two are noble gases. Helium is very small, very happy by itself. So that's why fluorine doesn't really got, a space or footing with that. And then neon gas is also quite happy on its own and is still fairly smaller than fluorine. And the other ones tend to react because they're a little bit larger, so their outer electrons are a little bit easier for fluorine to snatch off. So that's why it will still react with noble gases, even though noble gases be like trying to be bougie and don't want to be bothered with nobody. I ain't mean to come at them like that, but that's how they be. Under regular conditions, noble gas is not really messing with nobody. And the next video, I believe, was bromine. So this was kind of cool. I believe this video starts out with actually bromine in a gaseous state, and bromine gas is actually quite heavy. So even with its physical properties, bromine tends to turn into vapor quite easily. So even at room temperature, I believe the liquid becomes a gas. So that's why when they go to pour it, it's like this heavy bromine gas that you can kind of see leaching off of it. And bromine actually comes from the Greek word bromos, meaning stench. So it's kind of funky, as most of the halides are, and the stuff that they tend to make or compound with tends to have an odd smell. So that's why hydrofluoric acid tends to be kind of stanky. Hydrochloric acid tends to not smell so great, and the stuff that's dissolved in it. Yeah, there we go.
Readily to produce a reddish brown vapor. The vapor is denser than air We can see this by pouring out some of the vapor and seeing it settle. As since the bromine is less reactive than chlorine, we can use a little bit more reactive metal. We'll react the bromine with some aluminum in the form of aluminum foil. The aluminum foil gives us a large amount of surface area and increases the rate of the reaction.
I don't know why I was like sparks and stuff, but I love me a sparky reaction, okay? Astatine is one of those rare, it's extremely rare. And it decays quickly, so it tends to be kind of radioactive. So a lot, as you've noticed over the course of these weeks that we've been talking about the periodic table and its elements, there are the heavier elements tend to either not occur in nature, or if they do, they tend to be very unstable and very radioactive. So astatine is one of those, and it's considered one of the rarest naturally occurring elements on Earth. And because of its radioactive qualities, it has actually found use in medicine. So they tend to use these radioactive substances to tag and identify like cancer cells. For the most part, I think that's probably like the widest, the most common use for it in medicine is to identify cancer cells. Then you have they all form acids when they combine with hydrogen. So like I said, hydrofluoric acid is one of the most corrosive acids in existence, because fluorine is the most reactive and the most electronegative. So it makes a very, very, very strong acid when combined with just regular hydrogen, not in water, because you get those ion situation when you dissolve stuff in water. They're all pretty toxic. So even like iodine is toxic to an extent, but like I said, because it's a bigger element, it's not as reactive as fluorine. So I know you messed around and scraped your knee or something at Big Mama house, and she gonna pull out that brown bottle of iodine. You be like, "What's that?" And then she touch you and it's like, "Ah!" And you know, everyone scrape nothing else ever again at her house, because iodine is because it's so reactive and it's toxic. It kills anything that is in, near, or around. Like really, you're not really supposed to use it on open cuts. They tend to use like iodine when they clean the surface of your skin before they break the skin, because it is very good at cleaning your skin. Even I believe even more so than like isopropyl alcohol. So that's why they tend to use iodine. I think they're actually kind of getting away from that, but they do still use that to clean the surfaces of your skin before certain procedures and things like that. They readily combine with metals to make salts. So like I said, the sodium, you get the sodium chloride. So that's our favorite salt. Okay. That's why that happens. And once they form those salts, like I said, they tend to be neutralized and they're not as reactive. They have 7 valence electrons, which means they're one away from that happy noble gas number of 8, and that's what makes them so reactive. And they're all pretty reactive and electronegative. Electronegative means electron grabbing. Okay. And it sounds kind of counterproductive when you say negative. You think like, oh, against, but no, not in this case. It means grabby. And they are all diatomic in their elemental form. So fluorine, chlorine, bromine, iodine, astatine, they all exist in a 2 state. So F2, Cl2, Br2, I2, As2. That's how they exist when they're in their elemental form with themselves. And Hals is Greek for salt, and then gen is to make. So their name is well, their description, their group description of halogen literally means to make salt. So the fact that they make salts with all the other stuff and with metals and things like that makes them this happy little group. And they tend to also have these special conditions of like ionic bonding, which is basically where the ions, so like Na, excuse me, NaCl has an ionic bonding situation. So they aren't necessarily like covalent bond is basically like a sharing of electrons and they're hanging out together like this. Ionic bonding is not like that. Like I said, fluorine is extremely electronegative, so it's electron grabbing. So it literally snatches the electron off of the other thing, and it's walking around happy as a clam, but it now has a negative charge because it has this extra electron. And so the thing that it took the electron from is like, hey, can give me my electron back. So it's like following it around, trying to get its electron back, but it's like, nah, this mine now. You know, you snooze, you lose, like yoink, that type of situation. So that's what an ionic bond is where these oppositely charged. Okay, that's okay. Oppositely charged ions are kind of hanging around together because they have this opposite charge attraction going on. So that's an ionic bond. And a hydrogen bond, which tends to occur in things like hydrofluoric acid, for example. So in hydrofluoric acid, you have this covalent bond between the fluoride and the hydrogen where they're actually sharing the electrons. So ionic bonding tends to happen when it's making these salts with metals. And then covalent bonds occur when it's merging with other non-metal substances like hydrogen. So it has this covalent bond going on with hydrogen, but then also it has a hydrogen bond. So you have this HF molecule next to another HF molecule. And then the fluorine on one of those HFs tends to make this weak bond with the hydrogen on the other HF because you know, there's still that interaction between now fluorine has this slightly negative characteristic and hydrogen has this slightly positive characteristic. So it's kind of like ionic bonding, but it's with a hydrogen atom. So it's not quite the same. So that's why I gave it a different name. And it only occurs with hydrogen. So that's why it's called a hydrogen bond. And because of that, it actually makes solutions tend to have more of I would say a strong, like it tends to increase like the bond energy of certain types of things going on in solution because there's this extra bonding characteristic. So we experience this with all types of things like stuff with our DNA, our hair follicles, the cells within our hair, all like just all the cells in our body have these type of bonding situations going on. And so that's why we don't, you know, just fall apart when we get in the tub, is because our body is, you know, is tightly bound together with, you know, their regular like cell structure. But then there's also this hydrogen bonding and stuff that goes on. And when we drink stuff, we don't dissolve from the inside out and melt like, you know, the Wicked Witch of the West, because I guess she didn't have her hydrogen bonding together. But it's cool. I had some pictures of some stuff too. What was that one that I had where I had the iodine? Oh yeah, that was iodine. So iodine is important in our body for like a lot of stuff. And one of those things is like I don't know if that, because that probably wasn't like common now, but when I was a kid, they used to have like the commercials and things like that, or like, oh, this country needs your help, or these people need your help. And then, you know, sometimes you would see this lady that had this big giant like neck, like her neck was like really, really swollen. That is called a goiter. And so that is formed when your body does not get enough iodine for your thyroid to function properly. So your body makes certain hormones called T3 and T4, and it requires iodine to do this. When it cannot make those hormones, you end up with a goiter, or instead of getting like, that's like a severe case if you have like a goiter or like a really noticeable swelling in your neck from your thyroid, that tends to be like more on the severe end, the like problematic. But in minor iodine deficiencies, you could end up with like a swollen throat, trouble swallowing, a little, slight trouble breathing and stuff like that, because your airway is being blocked by your thyroid gland sits right directly on top of your air box, and it looks like this little butterfly structure right here. And so sometimes if you have like neck pain and stuff on, especially towards the front of your neck, it might be your thyroid. So to get rid of this problem, they started adding iodine to table salt. And so that's where you get the iodized salt from. Salt is not naturally iodized. It doesn't naturally have iodine in it. Fish do though. So like fish products, sea kelp, seaweed, things like that tend to have really, really high concentrations of iodine in it. So like sea moss and things like that, tons of iodine. So if you're worried about your iodine intake and you're using any of these type of products or you're eating these type of foods, you probably don't need to worry about it, because I'm pretty sure if you're eating them regularly, you're getting a sufficient amount of iodine. And fluorine. So fluorine is actually in our drinking water, and this has actually been the source for like a lot of debate, and there's been what do they call them? Protest groups against dosing water with fluorine. They've been around for like 10, 15, 20 years. So I know I was like in middle school or something when I first heard about the protest groups and stuff, and Greenpeace and all, those type of groups, they were actually lobbying to get fluorine taken out of the drinking water. But I want to say it's the CDC that's over stuff like that. Those type of people, those government agencies, they had all of these arguments for why fluorine is useful for being in the water and all of that. But really the only thing that they could say was it reduced cavities. But I guess like there is some new, I would say from 2019, there's a new research article published in, I believe it's the International Journal of like Health and something, but this is like a world like wide study. So it's not just like, oh, that's just in America. And like, no, they study, because like here in America is pretty much the only place where the water is dosed with fluorine. However, overseas, especially in European countries, they drink a ton of tea, and black tea has about the same amount of fluorine in it as the average amount of like that you would find in our drinking water here. So that's why they use tea as an example overseas, because they tend to drink a lot of tea. And so that being said, it has been found, and this is a study that they published 2 years ago, that fluorine is actually linked to a ton of defects and cancers. So like schizophrenia, Down syndrome. I believe it even said like certain types of like autism, kidney dysfunction, liver dysfunction, like all this type of stuff. And the thing about that is that our children are exposed to it from the womb. So we're drinking the water while we're pregnant, and then they drink the water when they're out, and we bathe in it and all that. So we're exposed to this fluorine from all levels of our body for the most part, and we have no say over it. Like it's the only quote unquote medicine or dosing without consent in America. And so that's one of the biggest opposition to doing that, is because we don't get a say so as to if this is put in our water or not. And then on top of that, it's actually pretty hard to get it out of your water. So if you have a regular filtration system, you are not removing the fluoride from your water. You actually need to have a specific type of filtration system that specifically says it does remove fluorine from your water. Most of these tend to be quite complicated, and you would actually have to get it like attached to like the piping and stuff under your sink and stuff. Like it's not one that you can just attach to your faucet head and things like that. That kind of filters out like other stuff, and other minerals and things like that, but not fluorine. And fluorine actually filters out better in acidic water. So that's slightly acidic, like a pH between 5 and 6, as opposed to being at the normal like 7-ish range. So even if you did have a fluorine filtration system, if the water coming in isn't acidic enough, you're still getting fluorine in your water. And then on top of that, in adults, only about 10% of the fluorine in the water is maintained in our bodies, but children, about 50% of the fluorine that they take in is stored in their bodies, which is why, you know, a lot of these defects and things that we're noticing more and more recently, especially among our children, is getting more and more prevalent. And now they have research that supports that could be a very viable source of the problem. And so what high concentrations of fluorine in your body does is it inhibits your sodium potassium ATPase. So ATPase is an enzyme that basically breaks down the ATP. So we talked about ATP. ATP is adenine triphosphate, which is the energy for your cells. For all of your cellular processes, they all use ATP. And so this enzyme comes and it chops the phosphate off and uses it to open up sodium and potassium channels. So the sodium potassium channels are what your cells need to create action potential. So when your brain sends a signal to your foot or your leg or something to move or something to do something, these channels are activated. And the ATPases is what allows that action potential to be created, and also to help them relax. So if the enzymes that's meant to energize these reactions are inhibited in some type of way, guess what's not occurring? Those actions. So yeah, so that's why, you know, those. Do you have that? Do you have the picture? It should be a picture of the guy standing up with like all of these like different things around him, because it's a long list of things that are affected by that. Here, let me see. I'll pull it up so I can look at this, and I'll just read the list off to y'all. Okay, here we go. All right, so these are, I don't know if this is a complete list, but this is the list that they mentioned in the paper I was referring to. And so from the top, in the brain, you have Alzheimer's disease, autism, Parkinson's disease, attention deficit hyperactivity disorders, cognitive impairment, depression and mood disorders, schizophrenia, Huntington's disease, Down syndrome, degenerative eye diseases, epilepsy. In your thyroid, you get hypothyroidism, which means that it impairs the function of your thyroid. So, like I said, fluorine ends up coming in and reduces the activity of iodine in your thyroid. So that's how you end up with the hypothyroidism. Airway hyperactivity, asthma, cardiovascular disease, hypertension, chronic obstructive pulmonary disease, allergic diseases, tumor invasiveness, and metastasis. So metastasis is basically the spreading of the tumor. So it going from your liver to your heart, your lung, your breast, things like that. Metabolic syndrome. Metabolic syndrome tends to be an underlying factor of obesity and insulin resistance. Kidney disease, chronic kidney disease. So this is not like acute. This is something that occurs over time. So by the time you're older and you think you didn't live your life well and you age improperly, then boom, you need a kidney transplant or dialysis and things like that. Colorectal cancer. This is intestinal cancer in your lower intestine. Kidney cancer, bladder cancer, prostate cancer, infertility, arthritic diseases, So remember, I was saying it sends these signals throughout your body, and then you have your arthritis is a symptom of those signals not making it to where they need to go, and also the breakdown of the fluid and things between your joints, because arthritis is essentially like your bone rubbing against bone. So the breakdown of your joints, which is a problem, and diabetes. So yeah, pretty much everything that's like plaguing the health of our country today seems to be tied to the fact that they've been fluoridating our water for, what is it, like 40, 50 years now? I forget when they started that program, but yeah, they're doing it. And they could very well be the reason why we're in the unhealthy state that we're in overall. We spend trillions of dollars on healthcare and medical care, medication, and the projection is that all of that will increase over time. So, like I said, that's why we do what we do here. That's why I'm so glad people are starting to get more aware of their personal health and taking control of their personal health and paying attention to boiling water. Distilling it could possibly do that. But imagine distilling all the water that you always use, not just your drinking water. Because like I said, your skin is the largest organ on your body. So when you bathe in it, that's also getting in your body. If you go to a hairdresser and they wash your hair, if they don't have a filtration system, that's going right in your scalp. So, the best solution would be to get them to stop dosing us. Yeah, that's why there's protest groups. I'm not sure if they're still active, but I know when I was a kid, they were very active and they were very vocal about the possible implications of it. And then, like, I think at the time, because they didn't know the medical repercussions of it at the time, the health repercussions of it at the time, they were mostly just protesting the fact that we didn't get a say. Like, you didn't ask us, hey, do you want us to put fluorine in your water? Like, no, they just decided to do that. So that, I think that was like the biggest lobbying point back then. But with this research that they dropped, they definitely got some firepower now. So I hope they definitely get that in motion and make it a movement, because I'm on board. I'll send them my monetary pledge for them to get the lawyers up in there. Because that's who really be lobbying, the lawyers. They be out there like, so because they know the words, they like to mix words around and stuff and make it sound like it's something different when they, they just, I don't know. I don't like the way you do that with the words and law and stuff. That's why I didn't bother becoming a lawyer, because I'm just like, y'all just doing too much. Why can't you just say what you mean and mean what you say? But then you do that and they still want to take your words and twist them. So I'm like, nah, I'm good. But that is, that's pretty much it for today. We went like way over. We had a lot to talk about. We talked about a lot. We learned a lot today. Yeah. I don't know. I got a slight headache, but I'm gonna end up chilling out, vibing out with some RockTrue beats in like 30 minutes. So it's gonna be all right. So that's the shameless plug coming up next with Marley King, RockTrue beats at 8 p.m. Eastern, 7 p.m. Central. Always with something that put the heat on your soul and the meat on your brain. So next week, hopefully, then as long as they don't send me another email saying that my delivery is delayed, then we can get into these experiments. Because just looking at the video, like they had like a little preview video, like what it looks like it's going to be real fun, and I can't wait to do that with y'all. And we can go over the chemistry of them again, so you can see it as I'm doing it, and it's not like just like some words. And we can get into the nitty and the gritty of those, and then we'll start digging into the transition metals. Okay, they got a lot of strange stuff going on. That little middle part, the long middle part of the period. Yeah, I know we skipped that, and we skipped it on purpose. Okay, so that long middle stretch, we're gonna go over those in the whole period. So we're gonna do rows at a time, because really it's only like 3 or 4 rows down where they're useful, and then after that they get real radioactive, and we don't really use those much. So yeah, we only got about 3 more weeks for that. So that is what we're going to start getting into, and then we'll go over that experiment. So we might end up with a bonus experiment next month instead. So that being said, yes, as always, rock truth or nothing at all.